So let's now proceed to talk a little bit about nuclear fission reaction. When an unstable isotope of a heavy nucleus is allowed to absorb a neutron, it may become so unstable that it splits into two smaller nuclei. For example, when uranium-235 absorbs a neutron, the following nuclear reaction happens. So here is an atom of the uranium element 235 is absorbing a neutron here. It spontaneously breaks down to give barium and krypton, along with 3 neutrons here and a vast amount of energy here. This reaction can proceed in 2 different ways. You can get bromine and lanthanum, or you can get tellurium and zirconium. Now, this is the reaction here that you want to talk about, and is depicted by this figure here. Recall that the stability of a nucleus of an atom depends on the ratio of neutron to protons. If the number of neutrons increases significantly, then this atom can become so unstable that it can break apart spontaneously. And this is exactly what happens here. This is deliberately done to make this uranium-235 nucleus unstable by allowing it to absorb a neutron. When this happens, the uranium-236 breaks apart spontaneously to produce a tremendous amount of energy, and this is called fission. Now the point to note is that whenever this reaction takes place here, 3 neutrons are produced. If there is a certain mass of uranium-235 is used, which is called a critical mass, and they can absorb these 3 neutrons, that can initiate what is called a chain reaction. And this is depicted here. Look, these are the 3 neutrons that are produced from the first reaction. If this neutron here is allowed to be absorbed by another uranium-235 atom, look what happens. It breaks apart to produce these 2 smaller nuclei here, and it produces a large amount of energy and 3 more neutrons. These 3 other neutrons here, each can be absorbed by another uranium-235 nucleus, and each of these in turn can give 3, another 3 here, another 3 here. And the same thing repeats itself down here and down here. So altogether, we will end up at 27 neutrons here. And if these are allowed to be absorbed by other unreacted 235 uranium nuclei, then a big chain reaction can happen and produce a tremendous amount of energy. This energy can be used in 2 ways. It can be used in nuclear reactors in a controlled way to obtain useful energy, such as in the generation of electrical energy. However, the nuclear bomb is designed to produce uncontrolled fission reaction to cause massive destruction. So that is nuclear fission, when a huge atom absorbs a neutron, becomes so unstable that it breaks up spontaneously to produce a huge amount of energy and smaller particles with neutrons being produced. If there's a critical mass present, then all of these neutrons can be absorbed to initiate a chain reaction that produces a tremendous amount of energy. The other reaction is called a nuclear fusion reaction. Now, in a nuclear fusion reaction, we are bringing smaller nuclei to make a larger nucleus. And the one that we are more interested in is when hydrogen atoms are combined together to produce helium nuclei. This is the reaction that takes place in our sun and the other stars. For this reaction to take place, you need a tremendous amount of energy. Why? Because when you try to bring the nuclei of atoms together, Because of the positive nature of the nuclei, it is difficult to bring them and fuse them together because of the mutual force of repulsion that they're experiencing. That is why it needs a lot of energy. Why it takes place in the sun and stars is because energy is being produced there, and that sustains that reaction. Recently, scientists have been able to do that, and they found something very interesting. They found that the amount of energy that is used to create this reaction is less than that what is produced. So this is a very encouraging sign. If scientists can continue to produce this on a global level, then we can generate energy that is clean, energy that does not entail the burning of fossil fuel. So this can help us to move away from the burning of fossil fuel that causes climate change. And of course, there are so many threats that are involved with energy change. We are all aware of that. Now we move on to something that's called half-life. We alluded to this when we talked about use of radioisotopes and nuclear medicine. We said that we need a radioisotope that has a short half-life. That means it will disappear very quickly from the body. Now, what is the meaning of half-life? Half-life of a radioisotope is the time it takes for half the number of radioactive nuclei in the sample to decay. For example, let us say a scientist has just recently prepared 1 million atoms of a radioisotope. And that radioisotope has a half-life of 5 minutes. What that means, after 5 minutes, half of these atoms there will decay to produce a new element that is stable. So we're going to be left with 500,000 atoms of the radioactive nuclei, but we will end up with 500,000 atoms of a different element that is stable. So we start with this new sample now, and we wait until 5 minutes elapse. We'll end up with half of what this is. So half of this will give me 250,000 nuclei of the radioactive elements still remaining there. But the other 250 that have decayed will become stable. So in all now we'll have 750,000 atoms of the stable isotope. Now, for another 5 minutes, what's going to happen? Half of these will break down, and we will remain with 125,000 atoms of the radioactive isotopes in nuclei here, and the other 125,000 will add up to this here, and will give me 875,000 nuclei of the stable isotope. Now, you can see as time goes by, the number of radioactive nuclei will gradually become less and less, and the amount of stable nuclei there will become more and more until eventually all of these will disappear, and then you'll end up only with the stable nuclei. Now, the one that I want to talk about here is radioactive iodine, iodine-131, that is used to treat thyroid cancer, that has a half-life of 8.70 days. That means that, just like I used the analogy before, if we started 100 grams of pure 131 radioactive iodine at time 0, after 8.0 days, we'll end up with 50 grams of radioactive nuclei along with the other stable nuclei. So let's look at this table here and see what is going on here. When you create your table, you will put the mass that you're starting off with here, and you will start with time 0 here. Some students make the mistake of putting the half-life at the beginning. No, you're starting at time 0. After the first half-life, you will remain with 50 grams of radioactive nuclei. And you can see the stable ones are there. So 50 grams of these will change to stable nuclei. And then after the next half-life, after another 8.08 days, half of these will break down. So you remain with that mass of radioactive nuclei. And of course, the number of stable nuclei will keep increasing there. So after another half-life, we'll end up with half of that, 12.5 grams. And then eventually here, another half-life, we'll end up with 6.025 grams of the radioactive nuclei. And it keeps going down like that until it expires, and then we'll end up with only the nuclei here. But some interesting we want to talk about here. Look at this. Students believe that the half-life changes. No. So what I advise students to do, or what they should do, start with 0. The first half-life is 8. Then add a second half-life to that, a third half-life, and they keep adding the half-life there all the time. So the first half-life is this. Then you add second half-life to that, you end up with 16 point that, third half-life, fourth half-life. Now I want to point out something to you about the rate of decay. Look, for the first half-life, which is 8.07 days, 50 grams decayed. So the rate of decay is 6.20 grams per day. The second half-life, now look what is happening. It's changing from 50 to 25. So the rate of decay will be 25 grams divided by its half-life, which is 3.1 grams per day. The rate of decay for the third half-life now is moving from 25 to 12.5. So we're taking 12.5, I divide by the half-life here, I can see that is the rate of decay. Look how the rate of decay changes as time goes by. Reason for that is that the number of radioactive nuclei gets less and less, and therefore the rate of decay decreases with time. Now you can look at it like this. There's another one here. Use a better, nicer colors here. So this is the half-life curve. If you want to plot the time here against the mass, you're going to get a curve like that. As time goes by, you can see that the mass of the radioactive nuclei decreases gradually with time. So here at the top here, you're having pure radioactive nuclei. But even if you get this radioactive curve here, right, and you didn't know the half-life of this, this is how you can calculate that. So here you have 100 grams. Go to the point here where it says 50 grams, come across here and go right down the timeline here, and you can see this is the half-life here. In this case, it will be equal to 8.0, whatever you say, 7 or something. So note what is happening. As this decays, the concentration of radioactive nuclei are getting less, but the concentration of a stable nuclei is getting more and more and more, until eventually the radioactive nuclei will disappear and you would only remain with the stable nuclei there. Now, look at what is happening here. This is the frequency of radiation. At the very beginning, when you have lots of radioactive nuclei, when the concentration is very high, the rate of decay is high. That's why the frequency with the radiations will come off will be high. As time goes by, the rate of decay decreases. Therefore, the frequency with the radiations are coming off gets less and less until it becomes 0 when we do not have any radioactive material there. And these are questions that relate to all the concepts that we have done. I've stated these in the solution manual. The answers and solutions to that can be found in the solution manual. I encourage you to buy that so that you'll see how the problems are solved and the answers are provided there for you.